let's think a little bit about some of the properties of alcohol. So the general formula for an alcohol we saw is some type of group or chain of carbons bonded to an oxygen, bonded to a hydrogen. And of course, the oxygen will have two lone pairs just like that. Let's compare this to water. So water just looks like this. You have a hydrogen bonded to an oxygen, bonded to another hydrogen with two lone pairs. Now, in the case of water, the oxygen is much more electronegative than the hydrogen, so it hogs the electrons towards it. So you have a partial negative charge at the oxygen end, and then you have partial positive charges. You have partial positive charges at the hydrogen ends, and that's what allows oxygen to that's what allows water to kind of bond to itself, or to kind of have not a ridiculously low boiling point. So let me show this. So let me copy and paste this, and we've seen all this before in regular chemistry. So copy and paste. So let me draw some more water molecules here, and let me draw another water molecule here. So you see water, because the oxygen end has a partial negative charge and the hydrogen ends have partial positive charges, the oxygen of one water molecule will be attracted to the hydrogen of another water molecule. And we've seen this before. This we call hydrogen bonding. So that right there is hydrogen bonding. Hydrogen bonding. The exact same thing can happen with alcohols, although alcohols really only have the partial positive charge on the hydrogen. We don't know exactly what's going on here. We probably have carbons bonded to the oxygen, and with the carbons, they're reasonably electronegative. They're not going to have their electrons hogged as much as a hydrogen would. So in the case of an alcohol, actually let me draw, instead of having this R for radical there, let me make it a little bit more concrete. Let me draw an actual alcohol. So an actual alcohol, maybe we have methanol. Maybe we have methanol. It would look like that. It has a hydrogen right over here. Oxygen is much more electronegative than the hydrogen, so you have a partial negative charge there, and then you have a partial positive charge there. So it too, because of these hydrogen bonds, it will have a reasonable boiling point. It won't just turn immediately into the gaseous state. It would actually try to bond to each other. So let me copy and paste that. So it can also form the hydrogen bonds, although they won't be quite as strong as what you see in water. And that's why something like methanol actually has a lower boiling point than water. It's easy to make it boil. It's easier to make these bonds break apart because you don't have as much of the hydrogen bonding. So this is an example of hydrogen bonding with methanol. Now, because methanol can have hydrogen bonding, and it has this slight polarity to it, and water obviously has hydrogen bonding, methanol is actually miscible in water. And all that means is that it's soluble in water in any proportion. No matter how much methanol or how much water you have, it is soluble. So if I were to draw some methanol molecules, maybe this is the water right here. So if you drop a methanol molecule right there, that would have a hydrogen bond right over there. If I were to draw another methanol molecule, maybe right over here, you would have another hydrogen bond right over there. And that's what allows methanol to be soluble in water. Now, as this chain grows, or if you have alcohols with longer radical chains, then they become less and less soluble in water. But their boiling points actually do go up. And let's think about why that is. So if I have something like, let me do butanol. So butanol is going to have 4 carbons. So it's going to be H3C, H3, let me just draw it like H3C, CH2, CH2, CH, let me do it like this. H2C, then that carbon, that last carbon right there is going to be bonded to the oxygen. It's going to be bonded to an oxygen, which is bonded to a hydrogen. Now, when you have a situation like this, the oxygen will have a partial negative charge. The hydrogen will still have a partial positive charge, just like we saw up here with both the water and the methanol. But now you have this big thing here that has no polarity. So this part of the alcohol is not going to be soluble in water, and it's going to make it harder for this part to be soluble over here. So this right here is less soluble. This is less soluble. It'll still be a little bit soluble. So if you have some oxygen here, you will still have a little bit of the hydrogen bonding. You still will have a little bit of the hydrogen bonding going on. But this part is kind of, you can imagine it's almost, it doesn't want to dissolve with the water. It is non-polar. And so this is, you could actually, for example, butanol in particular, it actually is soluble in water, but not in any proportion. So methanol is miscible. Let me write this. And this is a new word. I don't think I've ever used it before in the context of the organic chemistry videos. So the methanol is, let me write that in a brighter color since it's a new word. Methanol is miscible. Miscible, which just means soluble in any proportion. Soluble in any proportion. So I don't care what percent is methanol, what percent is water. The methanol will dissolve into the water in any proportion. If you look at butanol, it is soluble, but not in any proportion. If you had a ton of butanol, some of it would not dissolve in the water. So this is soluble. So the butanol right here is soluble, but not miscible, in water. If you have too much of the butanol, all of a sudden some of it will not actually be able to be dissolved. And if this was a decanol or something with a really long carbon chain, then of course it's going to be very non-soluble. I mean, maybe you might be able to get a couple of the molecules in the water, but most of them will not dissolve. Now, the other reason I hinted, look, the reason why the alcohols have a reasonable, not too low of a boiling point is that they're able to do this hydrogen bonding. But you would say, well, look, these longer carbon chains, these are going to have less of the hydrogen bonding going on. Maybe these would have lower boiling points. But actually, the longer the chain gets, these actually have higher boiling points. And that's because these chains can interact with each other. So the longer the chain, so longer R, or the longer R chain, I guess I could say, we could say the higher the boiling point in an alcohol. Higher boiling point. It's harder. You have to put more heat into the system, or the temperature has to be higher for the things to break apart. And that's because this is one decanol molecule here. Another decanol molecule might look like this. Maybe might look like this. You have an oxygen and a hydrogen, and then you have your carbons. So you have your CH, your CH2, CH2, H3C. So you have this other butanol here. And what the interaction between these two chains are, these are the van der Waals forces. So even though they have no polarity, so these guys are going to have some polar interactions. They're going to have the hydrogen bonding. We've seen that multiple times already. But these long chains, they're going to have the London dispersion forces, which are a subset of van der Waals forces, where even though they're neutral, every now and then, one of these might become slightly negative on one side. So you might have a very temporary, partial negative charge. And that's just because of the randomness of how electrons move. On this side of the molecule, all of a sudden, you might have more electrons over there. So you have a partial negative charge. And because of that, you're going to have the electrons over here they're not going to want to be there. So you're going to want to have a partial positive charge. Then you're going to have a very temporary interaction. That's a very weak force, much weaker than hydrogen bonds. But as these chains get longer and longer, as they possibly even get intertwined with each other and get close to each other, these London dispersion forces or van der Waals forces are going to keep propagating. So all of a sudden, maybe these guys are going to be attracted to each other, and that's going to disappear. Then these guys are going to be attracted to each other, and then that's going to disappear. And then these guys are going to be attracted to each other, and then that's going to disappear. And so you can imagine the longer the chain, the more of these type of interactions you're going to have, the more attracted they're going to be to each other, and it's going to be harder to break them apart. Higher boiling point. So those are just kind of the two big takeaways on the properties of alcohols. They are, especially smaller chained alcohols, are soluble in water. The very small ones are completely miscible. And the longer the chain you have, the harder it is to dissolve in water, but also the higher the boiling point. The harder it is to break them apart because you have these London dispersion forces.